Je suis Martina Pastorino, une doctorante d'INRIA d'Université Côte d'Azur, en co-tutelle avec l'Université de Gênes en Italie, et je vais parler de segmentation sémantique d'images de télédétection, combinant modèles graphiques probabilistes hiérarchiques et réseaux de neurones convolutifs profonds. Désolée, mais je vais faire le reste de ma présentation en anglais. So, after a brief introduction and a quick review of the state-of-the-art related, I will describe the proposed framework and show some experimental results. And finally, I will draw some conclusions. The addressed problem is the challenge of semantic segmentation based on deep learning methods in case of scarce but realistic ground truth maps. In benchmark datasets, we usually have spatially exhaustive ground truth maps, which means that every pixel is labeled. However, those are only benchmark, and in realistic remote sensing application, we usually have sparse semantic segmentation maps, such as that one, that typically do not represent the class borders. This is known to affect the spatial quality of the semantic segmentation maps resulting, and it is a major challenge in the development of a semantic segmentation method based on deep learning. The proposed solution is to build a novel approach consisting of a combination of a hierarchical probabilistic graphical model and deep convolutional neural networks in order to perform the semantic segmentation of remote sensing images. The idea is to exploit the several processing operations of a convolutional neural network that deals with multiscale information, such as pooling and convolutional layer, which naturally fit the multiscale graph topology on which hierarchical probabilistic graphical models can be built efficiently and effectively. The idea is to exploit this multiscale information contained at different scales in order to obtain accurate results while lowering the requirements in terms of quantity and quality of ground truth maps. In this framework, among the current approaches in the semantic segmentation of remote sensing images, on one hand, methods based on Markov random fields play a primary role. They can model multi-resolution or spatial contextual information depending on the underlying graph topology. On the other hand, deep learning techniques achieve state-of-the-art results. They can obtain very high per pixel accuracies and even efficiently reproduce the shapes of the objects segmented. However, to work well, they need very big datasets of spatially exhaustive ground truth, which, as mentioned before, are only available in benchmark datasets. Now, starting from the proposed framework, the overall architecture is based on three main methodological components. First, a fully convolutional network is trained with a very high-resolution datasets of remote sensing images. Its activations at different blocks are extracted and associated with the quad-tree topology. On this quad-tree topology, a hierarchical probabilistic graphical model is defined in order to model multiscale and spatial contextual information. Finally, random forest is integrated in the technique to link the information extracted by the fully convolutional network and the Bayesian inference structure of the probabilistic graphical model, which needs a suitable set of pixel-wise posterior probabilities. More in details, for what it concerns the deep learning parts, the networks considered are fully convolutional networks, which do not contain any dense layer and therefore are able to yield pixel-wise classification outputs with the same size of the input image. They have an encoder-decoder architecture, and skip connections were considered to collect the activations. The hierarchical probabilistic graphical model is composed of a hierarchical Markov random field to model multi-resolution information and a planar Markov random field to model contextual spatial information at each level of the quad tree. Therefore, Markovianity is considered both between the scales and within each level of the quad tree. Multi-resolution fusion is addressed by the quad tree topology. Now, what do we know about hierarchical Markov random fields on quad tree? They are causal, and therefore it is possible to use efficient and iterative inference algorithms. However, they do not model spatial information within each scale, and therefore we added a classical planar Markov random fields, which, however, are generally non-causal. And this is why, in the process, we integrated a neighborhood relation, which is based on a one-dimensional scan of each pixel lattice through a Markov chain. This is built by 4 zigzag scans and 2 Hilbert curve scans. The visit is symmetric, thus not bringing any directional artifacts, which can occur while integrating spatial contextual information over a 2-dimensional pixel lattice through a 1-dimensional pixel scan. Now that the whole probabilistic graphical model is causal, it is possible to use time-efficient inference methods, such as the marginal posterior mode criterion. This criterion maximizes the posteriors of the label of each pixel given all the observations, and it is based on 3 recursive equations. The hierarchical probabilistic graphical model performs the inference through input pixel-wise posterior probabilities, which are computed by decision trees ensemble, such as random forest. Now moving to the experimental results, the algorithm was validated with the 2 ISPRS 2D semantic labeling challenge datasets over the 2 cities of Potsdam and Vaihingen in Germany. They are datasets made of near-infrared red and green images with a spatial resolution of 5 and 9 centimeters per pixel, respectively. These are ideal datasets, which means that the ground truths are spatially exhaustive. Therefore, in order to approach the actual case of sparse ground truth, we consider several training conditions. At first, the full ground truth was considered as a baseline, and then we removed the percentage of labeled pixels, either randomly, as we can see in figure B, or in blocks, as we can see in figure C. And finally, we added morphological erosion. The model has 3 main hyperparameters: theta, the transition probability across the scales; psi, the path neighbor transition probability; and L, which is the number of resolutions. The transition probabilities are modeled through Baumann's model, which is a model that, through a parameter, defines that the probability that a pixel and its causal neighbor or its ascendant share the same label. It's a sort of concordance-discordance model. Several estimations of the pixel-wise posterior probabilities were considered as well for what it concerned the base level of the quad tree. On the base level of the quad tree, we just had the original channels of the image, so the IRG channels. And since random forest is non-contextual, the results for what it concerned the smallest class cars, were not defined enough. Therefore, we proceeded with other formulations of the technique. For example, we substituted these posterior probabilities with the posteriors of the output layer of the fully convolutional networks. Or, considering only the smallest class, we either substituted with the posteriors of the output layer of the fully convolutional network, or with the nearest neighbor resides of the posterior probabilities of the upper level of the quad tree, which contained activations from the network. Now, these are qualitative results of the proposed technique in case of 70% of removed labeled pixel in blocks, as we can see by the second column. And here is the comparison with the original ground truth. As we can see, the proposed approach, which is shown in the last column, was able to recover some class boundaries that were lost in the predictions of the unit, and the introduction of the spatial information given by the probabilistic graphical model is able to mitigate the sparse ground truths that were used to train the network, thus not showing any random spots between the various classes. And the resulting maps are visually regular and not showing spatial oversmoothing. These results are confirmed by the classification accuracies shown in this slide. The proposed technique in its 4 formulations was compared with 3 standard fully convolutional networks, UNet, SegNet, and DeepLab v3+, and with an approach proposed at the beginning of this year, which is called FESTA, in which the training of a fully convolutional network with an incomplete ground truth is handled with an additional regularization term. As it is possible to see, the proposed technique obtains higher results for what it concerns the average recall and the discrimination of the smallest classes, such as vegetation, trees, and cars. And these results are remarkably more impressive the more the training set is further from the ideal fully exhaustive case. To conclude, I presented an over-semantic segmentation method combining fully convolutional network and hierarchical probabilistic graphical model that addresses the challenging problem of semantic segmentation methods based on deep learning in case of poor ground truth data. The performances are quite accurate, especially in the classification of minority classes, and it obtains higher average results for what it concerns the recall with respect to the state-of-the-art techniques. This amelioration with respect to the standard fully convolutional network are more remarkable the more the training set is scarce and approaches the case of sparse realistic ground truth maps. And further perspectives are the addition of feed-forward neural network to substitute the ensemble learning parts and obtain an end-to-end architecture, and extend this approach to applicative scenarios such as natural disaster management. Merci pour l'attention.
Thank you very much. I like it very much. I have a question. You have 3 parameters for the hierarchical Markov random field, and then you have the unit backbone, or it's not a unit, it's a convolutional net.
It's a unit, yes.
So did you try different backbones, or did you just set for one and then try to improve it? So on which part do you think you spend most time to get the results? On the Markov random field part, or on the...
I actually tried the other 2 backbones. I tried SegNet and DeepLab v3+, which were shown back there. But the average results were lower than the ones of the unit, and therefore we proceeded to go that way. So we actually spent more time on the Markov random fields.
Excellent.
Thank you.
Just one, I missed one point. So in the scale of the image, you do not use a Markov random field, but planar lines. Hilbert.
It's a planar Markov random field.
Yeah, but okay.
And the scan is made as a Markov chain with 4 zigzag scans and 2 Hilbert curve scans in order to have causality, even in the planar Markov random field.
But, okay, I do not understand why you have to use this kind of planar narrative instead of classical one. Because of the construction of your hierarchy, or because usually for image processing, what we call Markov random field is a variety of in given pixel, given neighbors without any curves or end. So
yes, but if it wasn't causal, we wouldn't have been able to use the marginal posterior mode criterion for inference, which is time efficient and it's recursive and non-iterative. Thank you.
We move to last presentation. Thanks again.
Thank you.